Welcome to this morning's session. Before we begin, I should just remind people that we have a poster session this afternoon, which will be held not here, but in the QuICS space, the Computer and Space Sciences building on campus. Right after lunch, we'll have shuttle buses that can take people over there. If you were to walk, I think it would take about 20 minutes. And there will be snacks, and there will also be lab tours which depart from that same space where the posters will be. So the lab tours will depart from there at 2:35. And so I'd like to welcome our first speaker of the day, which is Michael Bremner from University of Technology, Sydney. And he'll be speaking to us about average case complexity versus approximate simulation of commuting quantum computations.
Good morning, everyone. Can everyone hear me okay? Thanks for showing up early. It's midweek. You know, we're getting to that grindy section of the conference now where it's getting harder and harder to get here early in the morning. I want to firstly thank the organizers for putting together a really fantastic workshop. Like, I was really, really happy to be invited to give a talk here, given there's so many great speakers talking about really interesting things. So it's really awesome to be here. I'm really enjoying it. So this is some work I've been doing with my ever-forgiving co-authors, Ashley Montanaro and Dan Shepard, on, well, the average case complexity, well, the relationship between average case complexity versus the difficulty of simulating quantum computers. So Ashley's at the University of Bristol, and as you heard, I'm from the University of Technology, Sydney, working at the Centre for Quantum Computation and Intelligent Systems, and Dan works for the UK government. Oh, and if you want to actually read about this, you can go to the archive and download our paper. I think there's a version 2 up there now. All right, so forgive me for this slide. I'm used to giving this talk to experimentalists, and I feel like I'm preaching to the converted a little bit here. But I guess a theme of this conference, or at least a lot of the talks of this conference, has been that we should be thinking about performing algorithms or designing things we can do on quantum computers in the relatively near future, okay? So what does that mean? We want to look at ways of designing algorithms or simulations or whatever, which can be used, which maybe don't need the full requirements of quantum computation, but yet nonetheless demonstrate some form of quantum advantage over classical computers. Okay, so again, this is a pretty old slide. So there have generally been 2 approaches, which has been the community, especially the experimental community, has been sort of taking to this sort of problem, which has been sort of, the first one which I call sort of the D-wave approach, which I won't just attribute to D-wave alone, and I don't want to criticize it either because I don't think it's that bad an idea, but the idea has been, build a big device with lots of qubits which work kind of okay-ish, do something like quantum annealing, and then try to solve something like hard classical optimization problems in NP, okay? So I put hard in inverted commas because they're not always hard. It's one of the things we've discovered, and but it's not a terrible approach because you want to do something with your very big system. This is a good first try of something to try and do. Now the other approach, which a lot of other people have been working on, is to say, okay, let's instead of building a really big thing, we build really small things and do it really well. Okay, so we want to build gates and qubits with really, really high fidelity, and then maybe we can do like a little tiny Shor's algorithm or something like that, like the Optics guys did years ago. Or do some sort of very small demonstration which you can sort of verify fairly easily. The other, generally that community is also saying, well, what we want to do when we scale up a bit is to try some small-scale quantum simulations. Okay, now there's a problem with that, which is which quantum simulations are the ones you should actually do? And that's a very unclear problem, a very unclear thing. All right, so, and that's basically what we're going to be addressing in this talk. So which quantum simulations are really beyond classical? All right, so I wouldn't be giving this talk if I didn't have some sort of answer, okay? Fortunately, a few years ago, Scott and Alex gave a really good answer to this sort of problem in the context of linear optics. So they came up with this Boson Sampling protocol, which we've all heard a lot about. Okay, but briefly I should just run through it so we're all on the same page about what it actually is. All right, so this is actually a picture I stole from a really cool recent experiment by the Bristol group. It appeared in Science, I think, about a month ago. So I definitely can't draw that well. I totally stole that picture from Science, just saying. So that's my attribution. So this is your linear optical system. And so what you do is you have a system of basic linear optical elements. You feed photons in, you run it through the circuit, and then you measure in the photon number basis. Okay, if you set things up right, basically the outputs should just be, you should just be measuring the occupancy of, having one photon or no photons at all. Okay, so you're going to get basically a bit string. It's going to be spit out of this device. Okay, and each one of these strings is going to come out with some probability p of x. Okay, now the question that they basically tried to answer is to, how hard is it to approximate this probability distribution output by these devices with a classical computer? Say the probability r of x. And so the question is, what happens if you can have r of x close to p of x? Okay, and so the answer they resolved is that basically you can't do this to within a reasonable additive distance measure if the polynomial hierarchy is infinite, the permanent anticoncentration conjecture is true, and the Gaussian permanent approximation problem is also true. Okay, so as to what those things are, you should check out their paper. It's amazing. Read about it. It's really interesting. Okay, so I've been, I don't know how many of you follow Graham Smith on Twitter or on Facebook, and he's been giving talk tips like the last week or so. I guess this is preparing the talk for this week. This is what I probably should have used as my title slide. So what I'm really talking about in this talk is boson sampling for spins. Okay, so we have come up with a basic generalization of the Anderson-Markov argument, which applies directly to spin systems. So the first thing that you should be thinking is, wait, isn't boson sampling kind of boson sampling for spins anyway? I mean, I can simulate boson sampling on my quantum computer. Quantum computers are made of spin, so, what are you doing? Like, what we've actually done is to develop basically a different protocol based on different sets of hard problems which underlie this system. So in some sense, it's sort of a logically independent problem. Okay, so I'm not just directly trying to simulate boson sampling. All right, so what are we actually looking at? We're going to, pretty much the whole talk is going to be about circuits which live inside this class, which Dan Shepard and I, one of the co-authors in this paper, have spent way too much time thinking about. So the class is called IQP. Probably a lot of you have heard about it. It's a very, very simple class. So the whole idea of us looking at this class of problems is because they seem like, or this class of circuits, they seemed like a really simple class of circuits which you could do things with mathematically, but nonetheless seem to have a lot of entanglement, could get pretty complicated, and is vaguely kind of physically interesting. That was our original motivation. So let me just run through what it actually is. So it's really a toy class of problems. Okay. Well, that was the way we saw it in the beginning. All right, so it's very simple. You can write them all like this. So you start with the all-zero state, as you normally do in a quantum computation. You apply Hadamard's on every qubit. Then you're going to do some unitary, which is diagonal on the Z basis, constructed from quantum gates. And then you're going to do another round of Hadamard's on everything and just measure in the computational basis. Okay, so this is a very low-depth quantum circuit. The overall unitary, so this unitary in the middle, UZ, can be written like e to the IH, and H is going to be a sum over tensor products of Pauli Zs and Pauli Is. Okay, so if you were to look at the overall circuit, which I haven't written down there, so you can sort of multiply this whole thing by the Hadamard's. What you're going to get is some unitary which is diagonal in the X basis, which instead of Zs here, you're going to get X's. Basically, that's what happens. That's what the total circuit looks like. So the circuit can be sort of represented as a whole bunch of, commuting gates, essentially. All right. In the problems we're going to look at today, this UZ is basically constructed from either things like square root of control Z gates and T gates, or there's another class which is sort of the phase type Toffoli gates, Z gates, and control Z gates. Okay, so they're very simple. Okay. All right, so what does this name mean? Instantaneous quantum polynomial time. It seems like almost a contradiction. So the polynomial bit kind of comes from the fact that the polynomial bound the number of terms in the above sum. Because of that, there are sort of circuits in this class, in principle, which could, basically be sort of polynomial depth. Okay. Clearly, each term commutes. The instantaneous bit comes from because in the measurement-based model, if you were to sort of allow free preparation of graph states, which is not really free, but imagine you could, there's a way of basically implementing all these circuits in a single round of measurements, okay? So there's no adaptation required. So back when we first started thinking about this, everyone was working measurement-based quantum computing, and this was sort of one of the motivations for looking at this class in the first place. All right, so what's IQP sampling? It's basically the same sort of idea as Boson sampling, except with a different class of circuits. All right, so you're going to have circuits that look like this. Okay, these are the two sort of generic things that I'm looking at today. So this first one, I don't know if you can read that, but the Hamiltonian, which represents the evolution of this circuit, is basically something drawn from the two-local Ising model. Okay, and then in this circuit class, like I said, it's basically the phase-type Toffoli gates, C phases, and Z gates. Okay. So the question we ask is, can classical computers approximate these sort of circuits in polynomial time? And the answer is basically no, if you didn't know what the answer was. All right, so we almost have a theorem. And I say almost a theorem because there's a conjecture which is still open. All right, so what is that? So what is the process? So again, I'm used to giving this slide to experimentalists, so I have to walk people through it. So what's the idea? For instance, we could randomly choose circuits from, well, this sort of class. I've written just the Ising model type here. So imagine you had the two-local Ising model, okay? So what we want to do is randomly choose the edge weights of the fully connected two-local Ising model. All right? In the set of circuits we analyze, just for simplicity's sake, we chose, you might be able to read this in e to the I pi of 8 up here. So we chose a particular weighting, or a set of weightings which you can possibly have, just for simplicity. And so what you're going to have here is like, you're going to choose weights on all the vertices and all the edges, which go between 0 and 7. Okay? And that gets you to wrap around the circle, and that's kind of important for our analysis. All right, so you randomly choose an Ising model from this set, and then what you're going to do is start your circuit in the L0 state, do an evolution according to this Ising model, which is diagonally x basis, and then measure on the computational basis, and repeat this polynomial many times. So, each sample that you take is going to have a probability which is just given by the usual rule, which is written down here. Alternately, you could randomly choose a circuit from this C-facing Toffoli set, which I'll have a picture of in a couple of slides. So what's the main result? It's basically that if either conjecture 1 or 2 is true, which I'll explain in a minute, then there is no efficient classical algorithm that can sample from any R of x such that it's close to, well, it's within a constant 1 norm distance from P of x, unless the polynomial hierarchy collapses. And the constant is 1 over 192, because Ashley is, he likes working out constants. I don't, he does. All right, so conjecture 1. Conjecture 1 is basically that the average case complexity of the complex temperature Ising model is sharp p hard. All right, so let me try and explain that a little bit. So up here we have a Hamiltonian, which is the Ising model. You can have edge weights and vertex weights, okay? In this case, what we're going to choose these edge weights and vertex weights to be is just some number between 0 and 7, okay? When I said we're going to randomly choose this Ising model, we're going to start with the complete graph, and then we're going to randomly assign edge weights and vertex weights from these numbers, from 0 to 7. And then what you can see fairly easily is that the amplitudes of circuits, which these things are associated with, are proportional to the square of the partition function of the Ising model for or the complex temperature Ising model of these things. Okay? And so it turns out that, well, the problem we want to be able to solve, which we don't manage to solve, is that computing a multiplicative approximation to these guys is sharp p hard for randomly chosen graphs. Okay? And this is really precisely what we need to be true. Now what you can show about this particular set of circuits is that it's definitely sharp p hard in the worst case analysis. Okay, so computing the partition function of these guys is to within a multiplicative constant like this is definitely sharp p hard. You can see our paper to see that, but there's also been recent work by Goldberg and Guo and Fuji and Morime, where they've basically shown this result as well. All right, conjecture 2 is to look at the complexity of the gaps of randomly chosen degree 3 polynomials. Okay, so what is that? So here's a degree 3 polynomial. So these x's can take value 0 and 1. So the problem is we want to compute the gap of this polynomial. So what is that? That's to compute the number of, the difference between the number of evaluations of f of x which go to 0 versus the number which go to 1. Okay? It was shown a long time ago by a paper by, I think it was Boson et al., that you can associate degree 3 polynomials with quantum circuits like this. And so the degree 3 terms up here are basically equivalent to C-phase gates. It's pretty easy to show this. And in which case the amplitudes of these things are proportional to the gap of these sort of polynomials. Okay, so down there. So the problem we come up with is very similar to the one or the conjecture that we came up with is very similar to the one on the previous slide, which is basically if you were to randomly choose these circuits, you get a randomly chosen degree 3 polynomial up here. And when I say randomly chosen, these alpha, beta, and gamma are just being chosen randomly from 0 and 1. Okay, so you're just coin flipping to determine where the gates go. The computing a multiplicative approximation to this gap is sharp p hard. That's basically the conjecture. Okay, so for those of you who have heard me talk before, you might be asking this question, didn't you talk about this stuff like 5 years ago? Haven't we known this for ages, that these IQP circuits are hard to simulate? Well, way back at QIP in Singapore, I think it was, I gave a talk about simulating IQP circuits, and what we showed in that talk was that multiplicative approximations of the output probability distribution to these circuits, if you could classically simulate them to within a multiplicative error, then the polynomial hierarchy would collapse. What do I mean by that? Okay, so your quantum system outputs a probability distribution P of x. Your classical thing has a probability distribution R of x. Okay, so when I say multiplicative approximation, I mean that their R of x has to lie within sort of a constant ratio of P of x. Okay, for C to be between 1 and square root of 2. And if you could come up with a classical algorithm that could do that, then the polynomial hierarchy collapses. So that's the only conditional statement in this theorem. Okay, so unlike boson sampling and the thing I'm talking about today, there are fewer other conditional statements. So you might be asking, why isn't that better? Well, the problem is because that sort of approximation is completely unphysical. Okay, what we care about is additive approximations, and these two notions of approximations are incomparable. And let me just explain that with a very simple example, okay? Consider two probability distributions. There's like half minus W, and let W be something ridiculously small, okay? And then you have another probability distribution R, which is just a half 0, okay? Now, the one norm distance between P, why did I not put R? That's meant to be an R. P minus R is equal to 2 times W. If we want P minus R to be ridiculous, to be less than epsilon, epsilon only has to be small, not ridiculously small, okay? So, it may not be, one way of doing this, say, would be to if this W is really small, you can well approximate P by R by just deleting the W, okay? And a lot of simulation algorithms do exactly this. So if you look at a lot of the quantum simulation algorithms for simulating quantum systems, like all the mirror and PEP stuff, that's exactly what they're doing. Okay, so however, if you look at the same distributions and to talk about whether one can approximate the other in terms of multiplicative errors, they cannot, because you can show if W is a positive number, which it is, and C is a positive number, then you can never satisfy this condition, because if one of these things is 0. Okay, so the two notions are really incomparable. And it's not really useful for our notion of approximations. The second reason, okay, and the more important reason is that we need to look at actually what quantum computers really actually do. And what quantum computers really actually do is they take a simple description of your quantum circuit, and what they output is samples from a probability distribution to within some sort of additive distance measure. I've written for the one norm here. So, the output samples x with probability R of x in time polynomial and, the circuit size and your desired error bound. Okay, so what's really important about this is that in our previous results, this sort of device, we have no guarantee that they could ever approximate, the set of quantum circuits we want at all, because we don't get that guarantee with quantum circuits. Quantum circuits only can be close to a given unitary in terms of an additive distance measure. Now, why is that? Again, so if you have a finite gate set, which we do in the quantum computing model, you can only ever get an approximation to the given unitary that you want, okay? That's one problem. So generically, if you're trying to produce any unitary or some sort of continuum of unitaries, you only ever get approximations to things. And they're going to be additive approximations. The second reason is more practical. If you have any sort of physical noise generated by, say, a CP map at all on your gates, then if you were to consider sort of noise acting kind of everywhere in your circuit, which is a reasonable assumption, every time you do a gate, there is going to be some noise. For every qubit, there's going to be some noise. Then the overall map, which your quantum computer produces, is always going to be some additive distance from the unitary you desired. And there's just no way around that. Okay. All right, so for this reason, you can only really think of quantum computers as producing things which are additively close to the unitary you actually originally desired. All right, so sort of why should you care about these results? Okay, from a CS perspective, what we've shown is that the average case complexity of these two conjectures, which I discussed, if it's sharp p hard, then quantum computers cannot be classically efficiently simulated without a collapse of the polynomial hierarchy. And in a sense, this improves on the Boson sampling result by sort of proving the equivalent of the permanent anticoncentration conjecture. You should also check out a paper by Bill Pfefferman and Chris Umans, where they sort of they instead improve on Boson sampling, in a sense, by proving the equivalent of the random self-reducibility conjecture. And then they have to give up, though, the anti-concentration conjecture part. So you should read that. It's a really interesting paper. Now, what's also really interesting and why you should care if you're a computer scientist is that our constructions can most likely be applied to other sharp p hard sets of problems. Okay, so our sort of proof technique that we use is fairly simple, and we think it can be adapted to other circuit families. From a physics perspective, we're giving concrete examples of circuit families which should yield hard to simulate quantum circuits, okay, with high probability if you sort of randomly choose them. They only require Ising type interactions for one set of these circuits, and hence they have very low depth and they're potentially significantly easier to build in certain spin type systems. There's reasonable error bounds, and okay, so on the flip side, they do require long range gates to do because we are drawing these things from the complete Ising model, but we kind of need them for a quantum speed up. That seems to be what everything says. So, that's just life. So that's the way it is. All right. Okay, so that wraps up my sort of summary of the talk. And now I'm going to get a bit more into the details or give you a bit of a sense of how we prove all this. All right, so what I hear from people a lot is, why can't I just simulate, my favorite quantum system instead of doing whatever it is you're talking about? Because that seems hard. It requires long-range gates and stuff. Well, you can. I'm not saying you shouldn't do that, because it's awesome. Simulate quantum systems. It's great. I'm a quantum physicist. I think that's a great thing to do. All right? And, this sort of brings me to what I'm taking to calling the Feynman gambit. Quantum simulation is classically hard because there are exponentially many outputs. Quantum probabilities seem to be inherently hard to compute. So, let's just build quantum simulators. It seems to be a hard problem. No one knows how to simulate my system anyway, so let's just build that. Okay, again, nothing wrong with that, but if you want to be rigorous about this, it's difficult. And why is this difficult? Again, I'm sort of giving this slide to the wrong audience. I mean, you guys aren't going to be as intimidated by this as experimentalists are. So this is kind of my spook the experimentalist slide. The problem with the Hamiltonian simulation argument is we don't understand the complexity of quantum systems enough. We really don't. We can't really point to that system and say, yeah, that's definitely going to be NP hard in the case that you have. So it's a complicated mess. So, okay, in this problem, we're focusing on the difficulty of approximating, quantum amplitudes. Okay, that's what you'll see in a few slides. But other things you might want to do is to, compute correlation functions from your system. That's actually a pretty good thing to try and do, I would suggest, if you could build your quantum simulator. Or you might want to compute the lowest energy eigenvalue or get something into the ground state or something like that. Well, that seems to be well, those of you who work on the local Hamiltonian problem, this is kind of fraught with danger, talking about this thing, because it's really a mess, Things can kind of end up in NP, or NP, or in QMA, and we don't really know the difference between all these things. And, in the approximate case, things get really, really interesting, basically. Well, I say interesting, it kind of gets even more messy. So if we want to talk about approximately simulating things, this whole diagram I had on the previous slide just really gets messy, okay? Because there's a lot of conditional statements about everything. A really good example of this is the ferromagnetic Ising model. Okay, so if you want to compute the ferromagnetic Ising model partition function, in the exact case, it's sharp pretty hard in the worst case analysis. Okay, but if you were to allow a multiplicative approximation, which is a really, really good kind of approximation, that's what you would like, okay? Then the complexity sort of collapses from being way up here to way down here, okay? So it's complicated is what I'm trying to say. So you might say, okay, I'm just going to build my ferromagnetic Ising model. Everyone knows that's hard to compute because the partition function is really hard to compute. It then turns out that there exists a really good approximation to those models. And this is kind of the problem that D-Wave has walked into, more or less. So, like I'm saying, this is complicated. Let's actually focus on that sort of problem a little bit more. So, the partition function problem in the complex temperature case is an example of a problem in gap P. And so gap P problems are really interesting in that they remain gap P complete under multiplicative approximations, okay, which is a really interesting feature. So for those of you who have read the really old quantum computing literature, we used to talk about this stuff back in the 90s a little bit more. Quantum circuit amplitudes are gap P. Evaluating quantum circuit amplitudes is a gap P complete problem. So gap P forms sort of a natural upper bound on the power of quantum computing. Okay. However, if you look at the problems that are inside the class sharp P, it can be shown, or was shown by Stockmeyer back in '83, that you can get good multiplicative approximations of these sort of functions inside the polynomial hierarchy. So this is a polynomial hierarchy. There's infinitely many, complexity classes between here and here. So gap P complete problems under multiplicative approximations live out here, whereas sharp P, problems inside sharp P go down here. So there's a difference between sort of the upper bound of these two closely related problems. I haven't really defined gap P. Gap P is just the generalization of sharp P, which allows you to have negative numbers. You'll see that in a couple of slides. So this brings me to Boson sampling. Scott and Alex had a really good idea. You see a difference in the upper bound of these two very closely related problems. And their idea was to exploit this, okay? So what they showed was that imagine you could have a good classical simulation of, Boson sampling type devices. That would imply that there exists a BPP to the NP machine, which could use these samples to evaluate these gap P complete problems inside the polynomial hierarchy. Whereas we know that this shouldn't be able to happen, okay, if the polynomial hierarchy is actually infinite. Okay, what was a really great idea they had to do this was to basically exploit randomness to make this proof possible to actually, say something rigorous. Okay, let me just tell you a little bit more about gap P and why it's related to Boson sampling and to other complexity classes. Okay, so back in the 90s, Fortnow and Rogers and Fenner et al. Demonstrated that computing the amplitude of a quantum circuit is gap P complete. How do you see that? Well, this is sort of a sketchy slide. So what are gap P problems in the first place? So imagine you have some Boolean function which goes from, bit strings to -1 or +1, okay? Now, given the circuit as input to the problem is compute the gap of that circuit, okay? So this generalizes sharp P. So in sharp P, that would be just like 0 and 1, basically. And the fact that there's a minus sign actually makes a slight difference to the complexity of approximations for this problem. Now, you can encode this problem in the amplitude of quantum circuit is basically the fact that you can encode this problem or this gap into the amplitude of a quantum circuit is not particularly hard to see, given it basically follows from the universality of quantum circuits. Okay, so you can create some quantum circuit such that you look at the amplitude, that you get some delta C on 2 to the n appears as the amplitude. The way you see that is basically, one way of sort of beginning the construction is to say you have like Hadamard's on either side of a diagonal circuit which encodes the Boolean function in the first place. Then you apply sort of standard reversible circuit constructions to, well, come up with a quantum circuit which can do this, basically. All right, so that was shown back in the 90s. So it turns out there's actually, so if you have a universal gate set, you could in principle construct quantum circuits which have gap B complete amplitudes. I mean, it doesn't help you because quantum computers can't really precisely evaluate these amplitudes anyway, okay? So what sort of has become apparent over the last, I guess, 7 years or so is that, okay, we're talking about evaluations of amplitudes, not actually evaluations of quantum circuits. So, we can do things like add in projectors and things like that as sort of a free resource because we're evaluating amplitudes, okay? And so we can do sort of post-selection on these circuits. And you can show that you can take these sort of circuits, do a bit of post-selection, and come up with another circuit family which might not be universal, but yet still nonetheless has gap P complete amplitudes appearing in them. So an example is precisely the linear optical circuits that Scott and Alex looked at. Another example is the IQP circuits. They also have this property. So now I'll give you a quick rough idea of what the actual procedure is and how we use Stockmyer counting to do this. All right, so say imagine we want to know the probability of the all-zero outcome of some IQP circuit up here. All right, so step one, you write the circuit, and we're going to use a BPP to the NP machine to help evaluate everything. Right? So you send that circuit description to your sampler. It spits out samples according to some probability distribution R of x. And we can analyze this, say, with Markov's inequality, and we get a bound on the distance between a random P of x and R of x for a randomly chosen x. Okay? We feed those samples into our Stockmyer counting machine, and it's going to spit back an approximation A to, well, R of 0. Well, that's what we're trying to do anyway. What you actually will get out, if you just analyze it like this, is to see that, well, the distance between A and, well, you want a distance between A and P of 0, but what you get out of this analysis is a distance between, or a bound on the distance between A and some randomly chosen probability from your circuit. So that's not really what you want, okay? That's not great, but again, this is sort of mimicking an idea that Scott and Alex had, is that you can instead ask the question, what if I added some randomness to that original circuit in the first place? We can then show that, basically run the same analysis through, and then the bound that we get at the end is not a bound on a randomly chosen P of x, the bound is also a bound on the probability that we wanted for a randomly chosen instance of the problem. Okay, so we can kind of switch the probability distribution that we're analyzing with Markov's inequality from being over the outputs of the circuit to being over the set of inputs to the circuit. And so that's basically the neat idea that we use. Okay, so we do this, we analyze it, we get out a bound on the thing that we're trying to approximate, and it looks like this. Well, then there's another step that you want to look at. So you want to know when, say, for instance, this gives you a multiplicative approximation to this probability, which we know is going to be like sharp P hard, or could be sharp P hard. Well, if P dash of 0 in this case is large enough, it actually is a multiplicative approximation. So is this the case in the random case is basically the question you need to answer. Similarly, and related to this, you get a collapse in the polynomial hierarchy if the same things are going to be sharp P hard on average over the probability distribution that you've chosen your circuits over. All right, so this is where we spend a lot of time trying to work out classes of circuits which have the right properties, okay? So it turns out that if you choose the class of Ising models that I've been talking about, that you can actually prove that these probabilities are always large enough on average, or a large enough fraction of them are anyway. So, you basically choose from the distributions that I introduced right at the beginning of the talk, and then you can show that this IQP sampling procedure always gives you with high probability a good multiplicative approximation to the partition function of these problems. Okay, and like I said, we focused on this class of problems because you can actually prove that for this class, the worst case probability, or the worst case complexity analysis of these class of problems is definitely sharp P hard. Okay. Likewise, we did the same thing with the degree 3 polynomials. This is also a family of circuits such that this IQP sampling procedure spits out a really good multiplicative approximation to the gaps of these degree 3 polynomials, which we conjecture is a sharp p-hard problem. All right, so now it's helpful to draw up these nice lists of things which tell you what you're trying to prove and what you need to prove. So boson sampling has a bunch of ingredients, and we sort of can go through checking them off and see to what extent we can prove things and not prove things. So some of the key ingredients are that amplitudes in the first place are sharp p hard to precisely compute. Yep, that's true for boson sampling. It's also true for many quantum circuit classes. Okay, IQP circuits are one example, but there's many, many more which will have this property. You also want to show that these properties are sharp p hard to multiplicatively approximate. Okay, so for instance, one way of doing it is to show that they have gap p complete for that class. Then what you want to do is, this is badly written. Basically, you want to show something like an IQP sampling procedure or a boson sampling procedure like the one I showed in the previous slides. And then what you're going to have to rely on is you need to prove again that this sampling procedure gives you a good multiplicative approximation for the thing you're trying to compute in the first place. Now, in the boson sampling case, they give a pretty good argument that this is the case, but in the end they had to, because it's a very difficult problem in the boson sampling case to show this, that there's, in the end they had to leave that open as a conjecture, basically. They showed a lot of evidence that this is actually the case, but in the end the actual ultimate proof didn't come out. In our case, we're just really, really lucky. So this IQP class, because everything commutes, it makes it possible to actually just sort of straight up compute that this thing anticoncentrates. And then finally, you need an argument that the average case complexity of these things over the probability distributions you're using is actually sharp p hard. Again, in boson sampling, there's a lot of evidence to show that this is possibly the case. In the exact, if you're not looking at multiplicative approximations for computing these permanents, then it is the case. In the case of multiplicative approximations, though, this problem seems really hard. All right, so like I said, the anti-concentration stuff came out really easily for these IQP circuits. Basically, the only tool we used was the Pauli-Zygmund inequality, which is kind of a standard measure concentration tool. And there's a lot of counting of roots of unity, basically, and that's it. And so, I don't know how many of you know Ashley, but Ashley's really good at doing methodical calculations. He just went through and calculated. He's like, oh, look, here's the answer. And we're like, great. All right. Where our analysis differs from boson sampling sort of significantly, or where the sets of problems look quite different, is what's known about the random self-reducibility of these sharp p-hard problems. So in the case of the permanent, it's been a really well-studied problem. A lot's known about it. In the case of the class of Ising models we're looking at, very little is known about the average case complexity of that problem, which is really weird given how much work has gone into analyzing the complexity of the Ising model. And I'll get onto that in a second. All right, so this, like I said, we have to leave, because we didn't manage to solve this, we spent a long time trying, we basically ended up having to make a couple of conjectures, which are the ones I had at the beginning of the talk. The average case complexity of these Ising model partition functions is sharp p hard, and that it's also sharp p hard for for computing the gaps of these degree 3 polynomials. All right, so, I should point out, which should be obvious, we're not making these conjectures completely in the blind. The reason why we've focused on these classes is because you can actually prove that in the worst case analysis, they're definitely sharp p hard. For instance, this Ising model, the set of Ising models we're looking at, was shown really recently by Goldberg and Guo that they're definitely sharp p hard. In fact, they looked at an even broader class of problems for this. So you can read their paper, or actually look at the techniques in our paper, and they're pretty much the same argument. Likewise, if you talk to a lot of physicists, they say, didn't Barahona prove this in '82 in the first place? What you're talking about is a spin glass. Surely that's sharp p hard to compute the spin glass problem. Well, if you go back and check what Barahona actually did, it's not actually a random case analysis. What he looks at is the worst case analysis of the spin glass problem. Okay, so yeah, basically you have to deterministically choose the edge weights in order to prove the mapping to sharp p hardness. Whereas in our case, you have to randomly choose it. Okay, then you look at the evidence against our conjectures. And, well, there's not any real evidence against it, but there is a difference between our problem and the permanent problem. The permanent problem, there's a lot known about the random self-reducibility properties of this problem. And I've said all that already. All right, so I'm sort of wrapping up now. I guess the really big question, to my mind, is that we have a couple of conjectures. They are actually quite hard to prove, but there are definitely other conjectures out there that use a similar argument, and we haven't gone through trying to find them all. You could definitely focus on other circuit classes, or even other classes inside IQP or the Boson sampling type model, in order to come up with different conjectures which might be easier to prove. So, there's Bill Pfefferman and Chris Uman. Here's a picture of Bill. He's here. If you don't know him already, go and find him and talk to him about it. They showed that if you take sort of universal gate sets, then you can, well, unlike having problems with random self-reducibility, you can actually prove this random self-reducibility conjecture, but you sort of pay a cost, and that the anticoncentration conjecture seems harder in that case. We think, maybe. I mean, basically they didn't manage to prove it, but it's not really clear. It's just a hard problem. So, that's another example of something you can try and do. So these conjectures can be played off against one another, and also, like I said, these problems change when you change the circuit class you're looking at. The reason for that is there are a lot of sharp P hard problems that can be associated with families of quantum circuits. The other way of doing this would be to look at, since our earlier work, there's been a lot of work done on, looking at circuit classes where you have an approximate multiplicative sampling type result. Okay, and pretty much all of these look like they could be reasonable candidates for proving an additive approximation result. Okay, so there's a whole bunch of these things here. Okay. So, what's next? Or, what have we done? We've sort of reduced this problem of violating the extended Church-Turing thesis to a technical question regarding the average case complexity of a couple of families of sharp P hard problems. I think what a really big question that people, should be looking at and are looking at is what can be shown with respect to average case complexity of quantum things associated with quantum classes. Okay, there's a lot of open questions there. Like I said, if you look at other classes of quantum circuits, it can be shown to have a Boson sampling type argument, and which other families of circuits within IQP can be shown to be classically hard within sort of out of their own bounds. Okay, and then finally, for the physicists out there, how do you build these things? Like, what's the best way of implementing an IQP circuit in your superconducting system? Okay, thanks.
Hi. Well, for the problems that you look at, if you take a simple one and you say there are certain classical cases where it's sharp P hard, but at how many bits does it become hard in practice?
Good question. Like 1. This is where it gets interesting. So for the gap P complete problems, you can show that just evaluating the sign of the amplitude, for instance, is gap P hard. So if you want to look at the probability distribution, which is a bit weird, right? So what you can do is a counting by search argument. So you can show that in polynomial time, you can adaptively change the circuits in order to get gap P hardness. So
Wait, are you saying with a 1-qubit quantum computer?
Oh, no,
I didn't follow you.
Oh, right. Are you asking about like the quantum case or the?
No, I'm asking about the let me try one more time.
Yeah.
There may be quantum computers built in the near future.
Oh, when does it actually become
interesting to know if they can outperform actual tasks. Now, NP hardness is an asymptotic result.
Yeah.
But I would like to know whether in practice some of the evaluations that you're talking about are actually hard for classical computers at 50 bits or 100 or 1,000.
A really good question, and I don't know the exact answer to that. But what I would say is that the current, for simulating, say, those Ising type things, my understanding is once you get to above 50 bits or something like that, like that's where the simulations really die.
Oh.
But like it's really hard to know, right? Because these things are changing all the time. But what we can say is like if you go back to like the beginning of the talk, I'm not going to bother going through those slides, is that additive approximation that we have is a constant out the front there. So the accuracy needs to, as the bit size grows, the accuracy of the classical simulation would have to get quite good. Well, actually, no, that's probably the wrong way of putting it. I mean, basically I'm saying, like, I guess it's around 50 bits, but I don't actually know. That's probably the best answer I can give.
People might care about the answer to that
Oh, no,
question.
I know. Like, but I don't know if you can answer it. This is the
Well,
problem.
no, you can answer.
Like,
Well, I mean, you can't give a mathematically rigorous answer, but you
Yeah.
can say what's the best algorithm does.
well, and the best algorithms, I think, is about 50 bits.
50. Yeah, I mean,
Like-
I'm not looking for rigor. I'm looking for,
Yeah.
a statement about what people can do. Because it's very exciting that you can
Yeah.
say that these very low-depth quantum
I'm
circuits
being-
can't be simulated.
I'm being nice on the 50 bits too. Like,
Okay.
so I know people who've done it, and the most they got to was like 30. But I'm going to say 50.
Okay.
Like,
Other questions? All right, let's thank our speaker again.